Good afternoon, everyone. My name is Ditte, and I'm very happy to be welcoming you to this webinar where we will be introducing operational modal analysis, the theory behind it, as well as some practical insights into performing OMA analysis in ARTeMIS Modal. And as you know, Anders will be leading the session, and before I hand it over to him, I would like to point out that we have disabled both the microphones as well as the chat function for this webinar. But you are of course very welcome to ask questions both during or after the presentation. So if you have questions, please use this Q&A function in the top menu here at the Teams window, and we will then make sure to go over all the questions after the presentations. So with that, I think I will hand it over to Palle to start the presentation. So thank you very much, and enjoy.
Thank you very much. Yeah, I'd like to say welcome also to this webinar here about operational modal analysis using ARTeMIS Modal. I think I'm going to use around 1 hour as usual on this one here. So let's see if this will be the truth in the end, but let's get started. So I would like to just go through the things I'd like to talk about here. First, there will be a short introduction to the topic, operational modal analysis. And then I will carry on with one of the, you could say, 2 things I like to talk about today. That's actually what good response data is that you could say that is our basis for operational modal analysis. And then after that, I will try to go through some of the things we can do in the software in order to both process the data, but also repair any damage that this data may have before analysis. And then finally, we'll look at some of the operational modal analysis algorithms in the software. So this is the idea of this talk here. And I would say, as usual, I'll just go through a few slides just to get everyone up to speed with what operational modal analysis is. And you can consider some kind of structure that is vibrating. This is in physical domain that we are looking at here now. What we can do is we can try to put some sensors on this structure here and then monitor over time how the structure is actually now vibrating in the points that we are measuring in and in the directions. And then we can use some modal analysis tools to separate, you would say, all the things that are measured at the same time here in physical domain. We can separate that into the different modes of vibration using modal analysis. And one of the visible, or the most visible thing is, of course, the so-called mode shape that tells us something about how a dynamic mode actually is behaving spatially when we look at it. This one we can animate, and it allows us to see how the structure vibrates in this dynamic mode. This is the mode shape. Besides that one, there is also a parameter called the natural frequency. That is the frequency where you say that this mode here likes to vibrate most. And then there is a final parameter called the damping ratio that tells us something about how fast this mode will die out if we just gave it one hit and then let it die out. Then the damping ratio tells us something about the speed or the rate that this vibration will die out. So this is the 3 parameters that is describing one dynamic mode of the structure. And there are typically many modes. And also in the measurements, normally there are plenty of modes to find for the modal analysis tools. There are different ways we can do this. If we can measure input and output, we can use something we call experimental modal analysis. If we can only measure output, response of the structure, and we cannot actually measure how this response has been generated by some input, then it's operational modal analysis that we will be using instead. And in this talk here, it is what we're going to talk about here. There are different tools, as I said, but they're all in some way associated with each other. We call, when you study the physical behavior of a structure, we do that with something we call operating deflection shapes analysis, where we look at how modes combined is actually giving us some kind of vibration pattern at either a particular frequency or over a period of time. This is ODS. Then if we measure the inputs and outputs, we use experimental mode analysis, and otherwise we can use operational mode analysis when we only can measure the response. So this is the way these three types of analysis, they are actually working together in some way complementary to one another. Operational mode analysis is something where we have to deal with that we do not know what is actually causing the vibrations. The excitation forces, they are unknown to us. The only thing we can measure is actually how the structure is responding to whatever forces that has been applied to the structure. So you can imagine that there are many things that are basically unknown to us. One thing that we have to assume here is that, first of all, that the system itself is a linear system, so it doesn't really matter if it's weak vibration or high vibration levels. The way that the structure behave based on these different vibration levels should be the same. We also have to assume that nothing is changing. You would say the dynamic system is not changing over time while we are measuring. So we assume that it's a time invariant structure. And we also have similar kind of assumptions about whatever is causing or how the input forces, they are actually looking. As long as we in some way can establish some kind of, you could say, filter, we call it excitation filter, that can shape Gaussian white noise, that is a completely flat noise, flat spectred noise or input. If this can be shaped in some way so that it actually resembles the excitation forces we cannot measure, then we can actually introduce it into this paradigm or this model that we are using in operational mode analysis. So you can assume, say that everything that in some way is broad-banded excitation can basically be used. That's why operational mode analysis is very good for analyzing structures like civil engineering structures, also aerospace structures, where we have some kind of broad-banded excitation available. It can be traffic, it can be wind, waves, whatever. Something that excites a broad frequency range. This is actually very, very convenient excitation forms for operational mode analysis. And with that said, then let's proceed a little bit to how we can actually do the actual measurement. When it comes to operational mode analysis, it is only responses we are measuring. So that means we are basically only measuring how a structure is actually vibrating. And we can do that with different types of instrumentation. Normally it will be accelerometers, but it can also be geophones that measure velocity. It can be strain gauges also. It can be many things. But in many cases, it is probably accelerometers that are used for this type of measurements. There are two ways you can do it. If you have enough sensors, or you have few measurement points that you want to measure, you can actually just put whatever sensors you have in those points, and then do a single measurement. And then that's it, you are over. You can just import the data and do an operational mode analysis. It can also be that you need to have more points in your mode shape measured than the number of channels you have. And if this is the case, then you will have to use multiple setups, as we call it, multiple test setups. In this case here, you have to place a few sensors in some points where the modes that you're looking for, they actually are having a good, you could say, amplitudes. Since different modes, they have different places where they have good amplitudes and different directions also, it's always a good idea to use more than a single sensor for these reference points. So we place a few of them in different locations, in different directions, And then the rest of your sensors you will put in some of the points where you like to know the mode shape, and then you start measuring. So now you're measuring these 3 locations here plus the 2 you have here. And then once you're finished with this measurement, you'll then move these sensors over here to the next location and repeat in the same way again, doing another measurement. And you keep on doing this until you have actually reached the end. You have measured all the different locations that you would like to know the mode shape. Then you have multiple setups analysis prepared in this case here. Let's just see, I have a single example here, a very simple plate. This is actually one that I made an analysis of on the last OMA webinar I had just before Christmas. And I think if I can find the software here, we can just have a brief look how that looked. It was this plate here with 10 channels, where we actually had then placed, as you can see here, 8 accelerometers here in this first setup here. We then had 2 locations here where we had reference accelerometers sitting. And then we did measurements, and we got a 1-minute recording in the 10 channels here. I only show 4 of them, the ones that are checked here, but there are 10 channels available for this setup here. And then after the first measurement, we moved the sensors. So now we moved them here to those locations here. Instead, we just kept these 2 reference sensors located in the same place as they were in the previous setup. And then we did a new measurement. And in this way here, we can now combine things, we can link things together, because we have 2 points that has been measured every time we have a new setup. And based on these 2 points where things should be the same every time, it enables us actually to now put things together in the end. So this is how it works when we have multiple setups. Let me see if I can go back here again. So this is multiple setup measurements. But otherwise, you would say the type of analysis that you will be doing after that is exactly the same if it's multiple or single setup. But there's just this ability that you can actually have more mode shape points than the number of channels you have available. There's another example I'd like to show also a little bit later, but that's because we need something where there is some kind of deterministic sinusoidal excitation. So in this case here, there's again a plate of aluminium with 16 channels, measurement points, but there is also a shaker that is actually shaking this structure here with a constant sinusoidal excitation that is 374 Hertz. And this gives rise to some challenges in the data that we will have a look at a little bit later. But this is just to show you this example here visibly, so you can see what it is. So let's go to the next major topic, I would say, of this presentation here. That is, we have this essential requirement, you could say, in operational modal analysis, and that is we need some good data. If we have good data, it's going to be a really nice pleasure of making the analysis. If we have bad quality data, it's going to be a long day. So it's a really good idea to pay attention to how can we actually make sure that the data we are feeding into the analysis is actually good. And what should we actually be careful about? And this is one of the things that I like to talk more detail about in this presentation here. There are some different requirements when it comes to operational modal analysis. I talked about it before also. You need to have some broad banded excitation. You need something that can excite all the modes that you have in the structure that you want to find. You can imagine that you're testing a large, I don't know, structure. It could be a bridge or something. But if the wind or the waves or the traffic is only able of, you say, exciting up to, let's say, 10 Hertz, and you want to find modes at 50 Hertz or 100 Hertz, this is not possible for you. You need to have something that can excite those modes that you want to find. So this is one of the critical things in, you would say, operational modal analysis, since we do not have control over the input forces and the way they are distributed, you would say, in frequency. it can give us some troubles because we really don't have the energy at the frequencies where we want to find the modes. So make sure that you have something that is broadbanded that can excite the modes. That's also actually the next bullet we have here. We need, of course, something that can excite the modes. Another thing we need to make sure of is that we have multiple input forces acting independent. So you can say, I'm trying to draw it here, that there should be many things affecting the structure at the same time, and they should be also independently doing this excitation they're doing. Because this is a requirement. If you don't get more than a single input, we will have troubles separating modes that are very close. Or if you have a symmetric structure, it's also very difficult because then you need different types of, you say, exciting the structure from different angles. Otherwise, you cannot separate two modes that are closely spaced that is vibrating at the same frequency. So we need multiple independent input sources in the analysis. This is normally not a problem. But you could imagine that you are using operational modal analysis to analyze data from an earthquake, for example. So we have a severe excitation of the foundation of a building, probably more or less in one direction also. This is a single input excitation, even though it's strong, the whole building is shaking. But it actually is a single input, and it makes trouble for us if we want to find the modes later on. So multiple independent input sources are critical. It is in many cases, again, for civil engineering or also mechanical and aerospace, it's not really a problem, but it's just something one has to pay attention to. Then, of course, there is also the issue about the time invariancy. We have to make sure that actually the structure is time invariant, and we should also aim for that we have some kind of stationary response, so we keep on having response. We can get this if the structure is persistently excited with random input, then we get this kind of stationary response. But this is another thing that we need to be careful about and checking up on. If we have a linear structure and we also have multiple independent input sources, then we actually end up getting some response data that is Gaussian distributed. So we will have a kind of a histogram that looks like this, where we have this normal distribution here. And this is actually what we are aiming for, because everything in operational modal analysis is based on that we are exciting a linear model with Gaussian white noise, and that the response we get out that we are analyzing is Gaussian distributed response. So everything has to be Gaussian, and we of course need to be able to check for that also, that we actually have that in the response measurements, at least to some extent. So this is some of the things that are, you could say, the requirements that we have to look for. There are different ways we can look at this when we look at response data we have acquired. We can do some analysis in time domain. We can call that time series analysis. And then we can also switch to frequency domain, and we can do some other types of analysis there. And both these are, you say, good to do, because in both domains you can see different things clearly and other things you may not see so clearly in that domain, but then you can switch to the other one. So we will try to look at what we can actually get out from looking at the time series itself. There is, of course, some visual inspection we have to do to check different things. We can also try to look at some statistical measures that can also tell us something about the quality of this data here. And then there is this histograms that I like to introduce also today, where you can actually also gain a lot of information by looking at those. And then you can switch to the frequency domain, and here you can check other things like stationarity, and you can also use the singular value decomposition of spectral densities to look for many, many different things. Something I have talked about in the previous webinar about operational modal analysis, and I will also try to touch it a little bit here. But let's try have a look here. One thing that is really important is that we try to aim for having stationary signals. And a stationary signal is one that just keeps on, vibrating and vibrating and vibrating. It looks very constant when you look at it. So whatever goes on in this signal here keeps on just having the same kind of level and intensity, you could say, in the time series all the way through. So when you look at a time series, it should look something like this. If it's you would say a random signal that we are studying. You can actually also have it mixed with things that we really don't like. Periodic signals, for example. This can come from different things, but something that is, for example, a sinusoidal kind of vibration that is forcing the structure at the same time. This is some of the unwanted things. And it's just something that repeats itself over and over again. This is a periodic signal. And of course, you can also have it mixed with a random signal, so you get something looking like this. But we should try to aim for this. So this is a critical thing. A stationary signal that looks random. One thing we should try to avoid in general is to use a transient signal. Again, an earthquake we talked about before. This is a transient signal. And this is one of the things that can be a troublemaker. It's a very short signal, and things can die out very quickly, and that can actually cause a problem also for the analysis we are going to do. We can also have a non-stationary signal where things are changing over time, and if it is the structure that is changing, then it's a problem. Then we can have a clipping. Clipping is where the top and the bottom of the signal is clipped because we are reaching the end of our digitizer's ability to actually acquire this signal here. This is also a problem because it actually clips the amplitudes so they become constant top and bottom. This causes problem later on, types of noise in the data. Then we have also things like outliers. It's also called intermittent noise. But it's simply that we have peaks, really sharp, high peaks occurring in the data. And this actually creates a lot of noise in the analysis, and is something that we should avoid. So if we have this type of sharp peaks here, we should do something about it. And we will try to do that later. But this is one of the problems that we typically can deal with, electronic noise and so on, that suddenly causes these type of very significant peaks here, or spikes in the data. So this is another issue that has to be dealt with. Then we have something called trends. They can be either linear trends, or it can be some kind of growing or decreasing trend of the signal. Here in this case here, it's a kind of a growing trend. We can see it best here in the transient signal that the mean value seems to be actually growing like this. And this is really a problematic thing because it actually creates troubles in the low frequency end of the signal if we do not care about it. So again, there are tools available that can help us. But the first thing to do is, of course, to detect we have a problem, and we can easily see that in a time series diagram if we have this kind of growing trend in our time series. Then we have the one I think we talked about at the beginning also, when you have some kind of periodic signal that is mixed with your random input. It can be from here's a power line pickup, as we call it, which is 50 or 60 hertz noise that can be picked up if you have bad shielding of the cables or other things. But it can also be other kind of rotating components that is acting while you're doing the measurement, and they will give rise to these harmonic peaks in the frequency domain that can be quite significant and therefore quite disturbing for the analysis. So again, something we need to be aware of and do something about if it's going to be very critical, the size of these. It's something I'll try to show a little bit later, how we can do that in the software. And then finally, we have also dropouts. This can happen if you have, let's say you have wireless sensors that are connected in some way over the Wi-Fi or internet or something, and then they are transmitting packages, each of them individually, to a server. Sometimes you have dropouts of some of the channels. They don't send the package, or the package is corrupt, or whatever it could be, and then you end up having actually some parts of your signal that is zero. And other channels may still be measuring something, but this will be a kind of a nuisance, because if you have too many of these in different channels all the time, when you start analyzing this type of data, you will get serious problems with the mode shapes, because here, if you analyze this, the mode analysis would assume that this is actually a zero mode shape component, which is not the case. It's just because there's no data available here. So that means if you have something that drops out once in a while in a channel, then you can actually have that mode shape component is going to be pretty bad. So it's something one has to be careful about. And of course, if you have too much of this, you should try to repair the signal simply by truncating the parts that are not correctly measured in all the channels. That will be a kind of a recommendation that I would give. But let's see then, this was the time series, you could say, looking at the time series. And we did that before in ARTeMIS also. We can just try to go back again, just to have a look. We could see here that here we have some time series data that seems to be quite constant around zero. So there's no trend in this one here to look at. So it looks reasonable, okay. But one of the things we can also do is we can try to actually select a channel here now, and then say this is then the first channel up here we now look at. Let's try to look at the channel data histogram. This type of window looks like this. It's a window that tells us something about how this time series or the amplitudes of this time series is distributed. So we can see here that if we separate the different amplitudes from the minimum to the maximum into a number of bins, and then just put in every time we have some kind of a sample, we put in that sample in one of the bins where it's belonging to, then we can see that if we have something that is normally distributed, most of the samples, they will actually appear here at zero. That means around the mean value. And the more we get out in the tails, the less data we have. So normally distributed data is, you would say, it's happening most of the time around the zero mean, or the mean value of this signal here. So therefore, a histogram that looks like this indicates that we have something that is normally distributed, which is what we would like to have. Let's go back here, because things might not always be like that. If you have a sine wave that you are sampling instead of a response of a structure, then your histogram will look something like this. Suddenly, instead of having most of the samples situated around the mean value, like for Gaussian distributed data, now most of the time you are either at minus or plus the amplitude of the sine wave. This is where you are most of the time if you are observing a signal like this. So that's why you have these two peaks here at minimum and maximum the amplitude, because it's either there or there you are most of the time. And you actually most of the time, or the least amount of time, you are around zero. So it's a completely different distribution you have in this histogram here when you look at a harmonic response. So you can use this kind of histogram here for many things, because it actually reveals a lot about the data that we are looking at. Something that you could say is difficult to see when you're just looking at a time series of millions of samples. Now things are compressed into these maybe 100 or 200 bins, and it just makes life easier for us to inspect this type of diagram. So let's try and see, because you can see here there is a list of things we can actually study in this type of diagram here. Of course, it should look something like this. We saw it also before in ARTeMIS that if you have a signal that is Gaussian distributed, it looks something like this. Let's go to the case where we have a signal that is now clipped. So it's clipped to the top and bottom. So that means that there is a kind of a constant maximum amplitude, and the same for the minimum here. You cannot exceed these two here because the clipping prevents it from happening. So what happens actually is, as long as we have data that is within the clipping region, it is actually nicely distributed like the top part of a Gaussian distribution here. But the minute you get to the edge, it is cut, of course, at plus minus the clipping threshold. And then there is also a kind of a pile up here in both ends here, because you have suddenly things that would have exceeded or gone below these clipping regions thresholds is now forced to be at that threshold level. And that means that you have a pile up of information there in this clipped signal here, and that gives rise to that you get these two taps here, you could say, or peaks in the end here. So when it looks like this, it is an indication that you have clipping in your signal. The same with if you have, let's say, outliers, you have some significant values, spike values. They are not happening very often, but when they are happening, they are really big. That also causes a trouble, because then you will have few very large amplitudes from these clipped or these outliers, and that gives rise to that you get some more volume out here and also here in the end or the tail of this distribution here, simply because you have few very significant amplitudes from these spikes here. So instead of having something that tends to zero in both ends here, you get some volume, as you can see here down here in these tails here of the histogram distribution. So this is a way also to study and see that you have outlier problems. Then we can go to the next. That would be this power line pickup, as we call it, or when we have harmonic components. And we already discussed it before. You have these two minimum and maximum amplitude peaks in the distribution of a sine wave. And when you start now finding the histogram of a channel that is mixed with sinusoidal excitation and random excitation normally distributed, then you get this kind of form here where it's going to be a little flat, like you can see here, but it's still it has a little bit of the two spikes here. It can be more or less, but it's quite easy to see that it is not really a normal distribution. You have something in both sides there that indicates that you have a mix with some sinusoidal excitation. And the last one is dropouts. And dropouts means that you suddenly have zero instead of having a sample. Then you become zero. So now you will have a huge collection of zero samples. And that gives rise to that you get this kind of tap here on top of the distribution here, because you get all these zeros in that bin there around the zero collected. So this is some of the things that we can get out from studying, you could say, these histograms here, how they are related to the different problems that we can have in our analysis data. Let's go here to let's see the next slide here. I'd like to show you here how it can look, if it looks good, and we already saw that actually before. Then we can also now see below here the histogram of this, very nicely normally distributed, as you can see here. And then if we go now to the next one, then we can see when we start getting into troubles. Let's see here. We have now something we call skewness here. So when you have a signal that is not anymore, you say, having equal levels positively and negatively around the zero mean axis, then you get something we call skewness. And you can see here that in this signal here, 0 is here, but it's like everything is hanging down here, so there's much more values to the negative side than to the positive side. So when you look at it here, it may be difficult to see that something is wrong in this signal if you just look at the time series. But if you look at the number skewness here, you can actually see it's a negative number. And when you look at the histogram, it becomes quite clear that there is much more information on the negative side here than on the positive side here. So in this case here, the histogram is actually really powerful to tell you that there is something wrong here. And skewness is really bad when it comes to doing operational modal analysis. It's really affecting the analysis in a negative way when this is happening. And it might be for different reasons it's happening. It may not only be, you could say, what's called errors, but it can actually also be a kind of a physical behavior of the structure that is measured. But it's just not good for the operational modal analysis that actually requires that we have normally distributed data. The other one is the one that we talked about before, harmonic excitation. This is actually data from this this plate I showed, the black plate with this shaker. Here you can actually see zoom in on one of the channels. You can really see there's a lot of constant kind of excitation here from this sinusoidal excitation. At the same time, there has been a tapping on the plate, which is causing these free decays that we see overlap with it here. But because of this significant sinusoidal excitation, we actually get these two tails here of the sine wave distribution, quite significant in this data here. And this is, of course, a problem. So this is some of the things that you can see from viewing this kind of data when you do the time series analysis. Let's go just to look at now the frequency domain, what you can get out of that, because you can actually get similar things or additional things when you study that. And one of the things is, if you look at a time frequency diagram, then you look at a diagram where you have time up here as this vertical axis here, and you have the frequency here. And as long as, if you look down here, if you have a stationary signal, then you can see that the modes, they are actually lying on a vertical line. They are not changing in frequency, and this is what we like it to do. I mean, that it should not change. If you go up here, we have something that is non-stationary. In this case, you can actually see that it's not a vertical line anymore. They are actually now skew in this way here. So that means that in this case here, the mode or the order of the rotating component or whatever it is we are looking at here is increasing in frequency as time is passing. And this is a non-stationary signal, and this is definitely not good for operational modal analysis, because we assume that things are constant throughout the analysis. And that means if we have a signal like this one here, this is a mode, for example, then the natural frequency that you will get returned from analysis will be some kind of average of what is going on here. And this is, of course, not desirable. So it's a very good idea to check if you have stationary conditions by using a time frequency diagram. Last time we had an OMA webinar, I talked a lot about the SVD diagram. I'm not going to talk so much about it today, but it's a really nice diagram to look at because you can get many types of information out of it. This is, for example, the noise floor checking. You can see where the noise floor is the first flat line you have here. Here, the noise floor is somewhere down here because there are nothing that is completely flat here. So here you can really see all the modes. You can also see how many independent inputs you have. And as I started out from, we need to have multiple of those. And if you can see that you only have a single significant singular value line here, it means that you only have a single input basically in your response data. And this is not desirable because it makes it very difficult to separate modes that are very close to each other. So it should look something like this in order to be, you would say, data with multiple input excitation. Let's go and see what we can do with data that have troubles, you could say. In ARTeMIS, we have a signal processing dialog looking like this. It is in, let me just go to the software, that's probably easier then. It's the first task we have that relates to analysis. So if we go here to this one here, we have this dialog here that allows us to process the data, the raw measurements in different ways. But it's all designed to make it as good as possible for the analysis that you would like to do in the software. So the first thing you can do, that is to try to remove the trend. Remember that the trend was, if you had a linear trend, it was a growing or a decreasing kind of trend of the mean value. This one here can actually be removed just by checking this checkbox here. And what happens is we are simply fitting a straight line to the data, and then we are subtracting this straight line from the data. We do that per channel. And in this way here, we then get any trend that is linear removed so that the trend is now 0. That means that everything is moving up and down around the 0 mean. If the trend is not linear, let's say it's a kind of a growing, so it's growing up in some way, then the way to remove that is to actually introduce a filter. So in that case, you would have to click on this one here, and then you will have to select a high pass filter. And then you need to select I normally use a very low order filter. I do not need a lot of slope in this filter here. I just need a little bit that can cut away everything that is around 0. And then let's say now we are at a maximum frequency of 2500. So if I put something like, I don't know, 10 Hertz here, I will remove everything that is from 0 and then on the way up to 10 Hertz in this way here. And that will be something like a slowly growing trend like this. That one will then be removed by this operation here. And that will dramatically help actually the analysis, that we get this low frequency thing away from the data. It's very often I do this. Also, if you have some high values around 0 Hertz at DC, it's a really good idea just to get rid of them by introducing a very low order and low frequency high pass filter. This is just one way of getting rid of that. Then there is the decimation also. That was another thing on our list. And this should also be done if you do not need to analyze your data up to, in this case, 2500 Hertz. If you only need to look for modes up to, let's say, 128 Hertz, then you should decimate the data and zoom in on the important part of your data. Again, a very important thing, especially if you work with parametric estimation, like SSI estimators, There's no need to spend parameters estimating something that you don't really need, just because it is in the data. So make sure that you are actually zooming in on the part of the data that is important for you. Let's see then, let's go back here, see if I can find the right, so here. Then we have touched these three here, how they can help us getting rid of things like linear trends and growing trends. There is also outliers, for example. And outliers is also something that, of course, is not desirable in the data. And here we have a tool that can help. Let's say we have, I hope you can see, is a little bit, there only a single, you would say, sample that is having serious spikes all the way up here, like you can see. But there is a tool that can inspect the different channels in the software, and then it makes a robust estimation of the standard deviation of the signal. When I say robust, it means that it's not accounting for the spikes, but it's trying to look at you say what most of the data is having of standard deviation. And by doing that, then we can actually find thresholds that we can use to get rid of these spikes we have here, the outliers. And then we have different ways of doing it, but normally you will simply remove the outlier from all channel. I mean, you'll remove the sample that has an outlier in one channel, but you'll remove that sample in all your channels so that you maintain any phase relations between the channels in your mode shapes. We can try to do this. I think I have some data here that allows us to do this. Let's see here. I can just close this project here and then just open something, a simple project that has some outliers. We can start looking at the data. And here you hopefully can see that there are some peaks here, around here, that are not looking like, you would say, data that how it should look like. So we like to get rid of these peaks that we have here. So what we do is we will have to go to prepare data, because it may be that we want to do some kind of, let's say, detrending or other things before we start the repair. So that's why we have put it here in this task here. One thing I definitely know I don't want to do now is to do SSI analysis, so I'll just disable that and then I'll run it. And the only thing I do now is actually detrend the data. So now you can actually see here, this is then the SVD diagram of the data that has all these outliers. And maybe you can observe there is a flat line here. So it's actually indicating that we have a kind of a noise level that is probably at this level here. At least we have a lot of noise generated because these spikes, they are really sharp in time domain. And if you have something that is really sharp in time domain, it's really flat in frequency domain. And that means every time you have a spike, you get more and more flat noise added to your spectrum. So that's why it's a good idea to get rid of it, because it can help on actually the noise in your specters. So let's try to see. We go to this repair tool here, and now it has already inspected this these time series we have here, and it may be a little difficult to see in the screen sharing, but there is actually indicates there's a green color here and also here and so on, that indicates that we actually have found these outliers here. And if we are satisfied with this, then we simply click the remove outlier and get this little dialog here. Here we have some options. We can remove the samples that has outliers from all the channels. That's the first one. We can also zero them out. So we keep the samples, but it's just put zeros in instead in all our channels. Or we can reduce it to the threshold that has been determined here if you want to do that. But let's just remove it completely here. And then we click OK. And now we can try first of all to, I think we should go and check the data, how it looks. It looks like this now. There's no outliers left here. Maybe you cannot remember how it looked before, but we can go back to the original data here. And then we can see the peaks here. And now we can see how it looks now when it has been cleaned up like this. So it's a very simple analysis that is quite powerful because it actually helps us reducing the noise in the specters that we are going to analyze. Let's see if we can try to do that quickly here. Maybe you can remember before there was a flat line here. Now it's gone. That means we have lowered the noise level in the spectrum in this way here. So again, simple repair that has to be done that can help a lot on the analysis afterwards. Let's see if I can get further here now. I think it was not my software that stopped this time here. It was actually the presentation. Let's go to it again. Where did we go? Yeah, we were here. Okay. So this was outliers, yes. And now we come to the next one I like to show. That is, how can we actually remove harmonic components, power line pickup as it's called also, but harmonic components in the data. And that can be done with another tool that we have in the software. Let's try and see here. Now I want to find this other example that we had, this black plate. So this is one of our examples. I can just load it here. Now if we now process this one here, just to have a spectrum to look at, then we can see that we have these significant peaks here from this rotating shaker that was on it. So especially this one here is quite significant. So the way to get rid of this is to first of all in some way indicate at least the biggest one here. And then you can do that either with something we call harmonic detection. Then we can sweep through the spectrum and we can try to find these peaks automatically. But in this case here, it's so significant that we can actually just do it manually simply by adding a peak indicator manually here. So I simply go here and then I double click to get this one here. When I have this one indicated here, I can start a tool called Reduce Peaks. And this tool allows me now to try to find all these peaks here, or a sequence of data that only includes those, and then project orthogonal to that sequence the data, so that what comes out of that is data that is now blind to this sequence of harmonic peaks. I allow that I have additional peaks reduced if I can find them. So that means if the software from what has been told here also can find these automatically, it is okay that it also remove those. So I will simply click the start button here, and now it will start, it will estimate a range of state space models, and then it will try to find the model that best describes the harmonic peaks we have in this data here. And once we have that model determined, then we can use that for this orthogonal projection I talked about. And you can see the end result here is after reduction of the peaks, you cannot see these peaks anymore. They are simply away from the data. The data is blind to them. It's not really a filter because everything else is maintained, but these peaks, they are gone. We can now save it and then use this data here in a modal analysis. And we can try to just start something here to get something running here. So this is harmonic reduction. This is another way to clean up and repair the data. so that it becomes optimal for operational modal analysis. And then finally, yeah, we have, I think I've talked about these types of methods many times. So this is why I selected today to actually spend most of my time, you could say, on this with the data. But of course, we can just go and make a short analysis of this data here that we just created now, that has no harmonic peaks inside. And we can go to estimation. When, let me go back here. When I activate SSI in this signal processing here, I can enable it here. I did that just before I clicked the button there. If I then at the same time select what estimator I would like to use, and that I like to use an automatic estimation also, it actually means that when I now go to estimation here, it is already done for me. I do not have to do much more. You can see already there is a list of natural frequencies, list of damping ratios. There is also a list of standard deviation of the frequency and the damping. And of course, there is mode shapes also to look at. All of this is already processed automatically by the software, which is because this special SSI method we have here is a really robust way of doing things automatically. And we use this method extensively when we do structural health monitoring, because it has some really good, you could say, features that allows us to do things in an automatic way. We can load the data and then automatically get modal parameters determined with a high accuracy. So this is one of the reasons why this is our favorite tool. But of course, we have others also. And we have, for example, the enhanced EFDD methods. One time we had a patent on this one here, but that's many years ago, and everyone else likes it so much that they implement it in Python and so on. But we still have it, and it is still a good, going strong methods that very easily can detect the modes if you have some significant peaks from these modes in your data. The tool here is most applicable for lightly damped structures, because these are the ones where you get these very significant peaks. The more flat your spectrum gets, the more difficult it becomes with the peak picking methods that are relying on that you can actually see a peak. So just remember that if you have difficulties with the specters are flat or not so easy to see, switch to the SSI methods, because it's a kind of a black box. It can actually measure or analyze the data, even though you cannot really see the peaks in a proper manner. So it's nice to have different tools in the toolbox, and that's why we favor our pro version of the software that has up to 8 different tools in parallel. And when you have these parallel tools, you can also now do a kind of a validation, because you have multiple results of the same mode. And here I'm comparing the first mode of EFDD with SSI. Here we can see overlaid animation of the mode shapes of this mode. We can here see the cross MAC diagram that tells us that these two sets of modes actually are the same mode shapes. They compare with each other. And of course, we can also take a look at things like the damping and the frequency in this list here and see how good they compare with one another. So there are many things you can do in this validation approach here also. So that's actually what I wanted to show you from the software point of view. Let's just go to a final remark. And I've tried to talk about how we can ensure that we get a good quality response data and how we should aim for having things that are Gaussian distributed. We can do some inspection visually, both in time and frequency domain. We can also use these histograms that we have introduced in the latest release we have. And of course, we have SVD and time frequency diagrams in the frequency domain. Then I tried to show you some of the tools we have for repairing data that otherwise will cause problems for us. That is for outlier removal and also removing harmonic components. And then finally, I think I just managed to show you a little bit of an analysis with the two types of OMA techniques we have in our software, and also how we can validate these results. So this is the end. I think if you need more information, then there are videos at our YouTube channel. This webinar will also go there sooner or later. We also have a website with a lot of information. And the next conference is the ISMA conference in Belgium that we will be having a booth at in September. And otherwise, we have another webinar on experimental mode analysis in September, at September 17, where we hope, of course, to see some of you again. Thank you very much for watching.